subject,
Yeah.
inshallah.
Yeah, inshallah. Thank you very much for inviting me and for having me today.
Okay, thank you so much, Dr. Zalila. So this is there's 8 students already joining with us. Inshallah, will be coming more. And I don't know whether our foreign students already joining with us. I think not yet coming, but one of our international students, he came from I forgot kan or Somalia or other part from Africa, but he's very active for during the subject. So hopefully he's joining with us. I will remind him again. For the next 15 minutes, Dr. Zalila will teach. So I hope all of you can listen, and also meanwhile you can practice after Dr. Zalila teach about matrix. About matrix.
Matrix.
Okay, so I will give the time for Dr. Zalila. Time is yours, Dr. Zalila.
Okay, thank you very much, Dr. Dia. Okay, Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera and good afternoon to Dr. Dia and to all of you, dear students of Mathematical Economics class, all the way across the ocean in Indonesia. Greetings from me, Zalila Osman from Universiti Utara, Malaysia, in Sintok, Kedah, Darul Aman, Malaysia. How are you today over there? Okay, I hope all of you are in good health and are always receiving blessings by Allah Subhanahu wa Ta'ala, the most merciful and the most beneficent. I'm very pleased to be able to meet you to share my knowledge on the subject of matrix algebra in this session. So today, as explained by Dr. Dia, I'm going to explain how to solve a system of linear equations using the matrix inversion method and also the Cramer's rule method. So without further ado, let me begin the class by sharing my notes, okay, in order to help you in following the talk better. Okay, I'm going to share my Word file. I'm preparing a Word file. Okay, I hope all of you can see the file that I'm sharing.
Yes, we can see it, Dr. Zalila.
Okay, thank you, Dr. Dia. Okay, I will start now. So solving a linear equation system, matrix inversion and Cramer's rule method. Okay, let me, I think I can put this aside. Yeah, okay. So today I'm going to explain to you a system of linear equations in 2 variables and also a system of equations in 3 variables. How we can solve it using the matrix inversion method and also the Cramer's rule method. Okay, since I think probably Dr. Dia has been able to cover all the basic matrix operations like summing, subtracting matrices, and then multiplication of matrices, and so on. I think this you can follow the lecture. Okay, so given a linear equation system in 2 variables, x1 and x2 as follows, so we may solve this system using the matrix algebra method. Okay, written in the matrix array form, we have A11 x1 plus A12 x2 equals to B1. And the second equation, A21 x1 plus A22 x2 equals to B2. So expressing the system in matrix equation form, we have matrix A times matrix X equals to matrix B. So X is actually a vector, vector meaning this is a column vector, okay, 1 column, 2 rows. Okay, B is also 2 rows with 1 column. Okay, so in short, we can express the matrix equation above as AX equals to B. So solving the matrix equation is quite easy. So if the inverse matrix denoted by A to the power of -1 exists, the pre-multiplication of both sides of the equation by the inverse matrix will yield this identity matrix times X equals to the inverse matrix times B. So an identity matrix, when we multiply with X, will not change X. So now actually we have the solution to the linear equation system, which is X bar equals to A inverse, the inverse of A times the constant vector. So, okay. Okay, by definition of the equality of matrices or vectors, so this equation 1 shows the set of values of the variables that satisfy the equation system. Also, since the inverse matrix is unique if it exists, okay, there is only one, yeah, the inverse matrix, there is only one of them. The solution must also be a unique vector of the solution values. So we can write, yeah, the X vector as X bar. Okay, so I have already put X bar there. You can also put X star, yeah, to indicate that is a unique solution. There will be one value for X and one value for Y. So for the matrix equation form, we have a method for testing for the existence of the inverse matrix. So this is the advantage of solving a linear equation using the matrix method, because it provides us with a way for testing whether solution exists or not. Yeah, if we are solving a system of equations using the elimination of variables method, okay, we don't have a method for testing for the existence of the solution. So we might work all the way through, and then at the end, we will find out that there is actually no solution. But using the matrix method, we have a way of testing whether a solution exists or not by using the concept of determinant. Okay, so before that, okay, if matrix A has an inverse, then it is said to be non-singular. A matrix that does not have an inverse is said to be singular. So we can test whether a matrix is singular or non-singular using the concept of determinant. If the determinant that we calculate for matrix A is equal to 0, then we say matrix A is singular, meaning no inverse matrix exists, then there will be no solution to the system of equation. Otherwise, if the determinant of A is non-zero or not 0, then we say matrix A is non-singular, meaning the inverse matrix exists. Okay, we have a formula for the inverse matrix, which is equal to 1 over the determinant of A times the cofactor of A transpose. So in symbol, we have 1 over the determinant of A. We have two parallel lines, on the left and on the right of A. It looks like absolute value, but it actually means determinant. Okay. Okay, so using this formula, we can see that, okay, if the determinant of A is 0, so 1 divided by 0, it's undefined. That means there will be no solution. So if matrix A is singular matrix, meaning the determinant is 0, then there will be no solution. On the other hand, if the determinant is not equal to 0, so we can, there will be inverse matrix for matrix A, so we can obtain the solution. Okay, using this formula. Okay, remember in the previous equation, we have X equals to the inverse of matrix A times P. So the solution will be 1 over the determinant of A times cofactor A transpose times B. So if we have all these three components, then we can solve the matrix equation easily. Okay, so I'm going to just show you very quickly each of the three components. So find the determinant of matrix A. So we can start with a 2 by 2 matrix. Okay, so let's see, matrix A has these 4 elements. So the determinant is calculated by multiplying the 2 elements in the principal diagonal, A11 times A22, minus the product of the 2 of principal diagonal items. Like this, A11 times A22 minus A12 times A21. So for example, given A equals to 1, 2, 3, 4, then the determinant is equal to 1 times 4 minus 2 times 3, or equals to 4 minus 6 equals to 2. So we compare this with 0. This is not 0. So we can conclude that the inverse matrix exists. Okay, to find the inverse matrix, we need another component, which is the cofactor transpose. So for a 2 by 2 matrix, okay, we can find the minor first of each element. Okay, so the minor will be obtained by deleting the row and deleting the column where the element is located. So for example, for M11 or minor of element 11, it is found by deleting row 1 and column 1 of matrix A and taking the remaining element. So we can do that for the rest of the elements. Okay, I'm just going to go to this matrix in numbers, yeah. So for example, to find the minor for element A11, so you delete row 1, column 1, then you are left with 4. So this is the minor, okay, for element A11. Okay, for element A12, so you delete row 1, column 2, so you are left with 3. Okay, so you can do that for all the 4 elements, for the rest of the 4 elements. Okay. Okay, so finally, what you get is, okay, 4, 3, 2, 1. This is the minor of matrix A. Okay, but we don't want the minor, we need the cofactor. So to find the cofactor, we adjust the sign of the minor according to this formula. So the relationship between each cofactor and minor will depend on the value of the sum of I and j. So for example, if I plus j is an even number, then the cofactor will have the same sign as the minor. On the other hand, if I plus j is an odd number, then the cofactor will take the opposite sign of the minor. So for example, for C12, okay, cofactor is actually a matrix also. For okay, so for C12, substitute 1 and 2 into the formula, then you'll get minus 1 to the power of 3. Okay, so minus 1 times minus 1 times minus 1, so you get minus 1. So minus 1 times the minor of 1, 2. Okay, so that we get the cofactor will take the opposite sign of the minor. Okay, so I have shown here all the 4 cofactors. So putting that into the cofactor matrix, then this is what it looks like. Yeah? So we need to adjust the minor according to I plus j, the sum of row plus column. Okay, so this is what we'll get. 4 minus 3 minus 2, 1. Okay, next. In the formula, we need to transpose. So to transpose, we just change the row into column and column into row. Okay, this is what we will have. Yeah, 4 minus 3 minus, sorry, 4 minus 2 minus 3 and 1. The cofactor transpose is also called a join A, a join of matrix A. This is another name. So finally, find the inverse matrix using the formula since we have the component already. So that means, okay, you can write the determinant and the cofactor transpose. Okay, then you will have this as the inverse matrix. Okay, but for a 2 by 2 matrix, we know, I think you know already how to get the cofactor transpose using a shortcut, yeah? So for example, A equals to 1, 2, 3, 4, same matrix as before. So only 2 steps are required in order for us to get the cofactor transpose. In step 1, we exchange the place of the 2 elements in the principal diagonal. And then in step 2, we multiply the other 2 off principal diagonal elements with minus 1. Therefore, for matrix A, cofactor A transpose is equal to, okay, we exchange the 2 elements in the principal diagonal. So you exchange 1 and 4, yeah? So their places will be exchanged. And for the other 2 elements, there is no need to exchange their places. Instead, you just multiply them with minus 1. So this is what you get, yeah? So this is the same as the cofactor A transpose that we get earlier using the rather longer method of finding it, meaning finding the minor and finding the cofactor and then transposing. So shortcut is only applicable for 2 by 2 matrix. For 3 by 3 matrix and higher order matrix, meaning 4 by 4 or and other and higher dimension, we have to find the cofactor transpose by the longer way, yeah? Meaning finding the minor, cofactor, and then transposing. No shortcut is available for matrix other than 2 by 2. Okay, now this is interesting. Okay, I'm going to show you an economic application using the inverse matrix method. Okay, so for example, okay, when we want to solve a market equilibrium, okay, for price and quantity in a certain market. Let's say we have a market for shoes, for example. So we are given the demand function and the supply function. Okay, so the demand function is expressed as P equals to Q, and then the supply function is also expressed in terms of price and quantity. Okay, so we want to find the value of P and Q that will satisfy both demand and supply simultaneously. Okay, so let's try to solve this system of equation using the matrix method, specifically the inverse matrix method. So in step 1, okay, before we can use the matrix method, we need to arrange the equations in the matrix array form, meaning all variables to be solved must be put on one side of the equation, all constants on the other side. So from equation 1 and 2, okay, let me put it 1 and 2. Okay, so from equation 1, okay, we need to bring Q to the left-hand side like this. So P plus 0.5Q equals to 20. We just leave the constant on the other side. In equation 2, okay, we also bring Q to the left-hand side. So it will become P minus 3Q equals to minus 78. So now this is already written, not eaten here, written in the matrix array form. Okay, next we transform this into the matrix equation, AX equals to B. So this is what it looks like. We have the matrix of coefficient A. Okay, you take 1, 0.5, and then 1 minus 3, put it here. And then the vector of variables, P and Q. Okay, since we are arranging P first and Q second, so this is the arrangement. And for constant, we have 20 and minus 78. Right? Okay, so each of the matrix will be written there, are written there. Okay, in step 3, we need to test for the existence of a solution. So find the determinant of matrix A. Okay, so find the determinant. Okay, we know already how to find this. Okay, just, okay, I didn't show it here, yeah. Okay, like this, 1 times minus 3 minus 0.5 times 1. Yeah, it's written here. So it will become minus 3 minus 0.5 or minus 3.5. Okay, so since this value is not equal to 0, so we conclude that the inverse matrix exists and we can proceed to find the solution of the system. In step 4, find the cofactor transpose. So we can use the shortcut since we know that we can use the shortcut for 2 by 2 matrix. Okay, so CAT or transpose, cofactor A transpose, just exchange the 2 elements in the principal diagonal, so minus 3 and 1. And for the other 2 elements, we multiply by minus 1. This is what we will have for the cofactor transpose. In the final step, okay, we put the values that we get into the formula. So X is equal to 1 over the determinant of A times cofactor A transpose times P. All right, this is what we will see. Okay, now you can choose to multiply 1 over the determinant with cofactor A transpose to find the inverse matrix first, or you can do it in another way by multiplying the 2 matrices first. Okay, like this. So for myself, I prefer to multiply cofactor A transpose with the constant first and then get this sum rather than multiplying the 1 over the determinant with cofactor transpose, because then you will end up with fractions, yeah, for all the 4 elements, and then you need to multiply those fractions with the constant. That will be a bit messy, I think. Okay, so once you get this sum, okay, then you can multiply with the parameter outside, yeah. So 1 over minus 3.5, you can multiply with each of the elements, so you will get this value 6 and 28. Okay, so we can conclude that the equilibrium price is $6 and the equilibrium quantity is 28 units. Okay, so as you can see, matrix algebra method provides us with another way of solving the demand and supply function. That means equilibrium value of price and quantity in a certain market. Okay, next. Okay, I'm going to show you a system of 3 equations and 3 variables. I hope you have also start on this, yeah. So okay, I will explain from the beginning also. Okay, we have 3 equations in 3 variables like this. So all variables x1, x2, and x3 have been written on the left-hand side. So all 3 equations are in matrix array form. That means all the variables to be solved are written on the left-hand side, and we have the constants on the right-hand side. So putting this in 3 matrices, we have matrix of A or matrix of coefficients, and vector of variables and vector of constants like this. Then the system of equations can be expressed in matrix equation form as AX equals to B. Okay, so again, if the inverse matrix of A exists, then we can solve, yeah, using this solution. X equals to the inverse of matrix A times B. Okay, remember, we need to test for the solution using the determinant. So for 3 by 3 matrix, finding the determinant will involve okay, we can use, yeah, this is one way of finding the determinant using the Laplace expansion method. Okay, actually there are other ways, but I'm just going to show you Laplace expansion method. So the determinant can be calculated using any row or any column. You can choose to expand. That means you can use to find the determinant using the expansion of any row or any column. Okay, usually we find the row or column that has the most 0 or 1, because then the calculation will be made easier. Okay, if the element is 0, then we don't need to calculate that, because 0 times the cofactor will be 0. Okay, so that one will drop out from the calculation. Okay, so to find the determinant of A, okay, I'm just writing this, the determinant of A, so we can repeat again all the elements like this. So by using the expansion of the first row, okay, in the first row we have A11, A12, A13. So the formula is A11 times the cofactor of that element, which is C11, plus A12 times cofactor 12 plus A13 times cofactor 13. Okay, meaning each element in the first row is multiplied by its cofactor. Next, we change cofactor into minus. We express the same formula using minus. Okay, remember when we have cofactor and minus are related, yeah, using this formula. Cofactor is defined, this 3 lines meaning identity. So the left hand side is equal to the right hand side. Cofactor is defined to be minus 1 to the power of I plus j times the minor. So again, remember, when the sum of I plus j is an even number, okay, nombor genap, okay, then the cofactor will take the same sign as the minor. If I plus j is odd, then cofactor will take the opposite sign of the minor. Okay, so for example, when CI2, okay, we have minus 1 to the power of 3, then we have minus M12. This is what we have seen earlier. Okay, so in terms of this formula, okay, you can change C12 into minus M12. Okay, so instead of writing A12 times minus M12, we just put the minus sign in front of the number, in front of the element, yeah, to make the formula tidier or easier to understand. So that's why we have the minus sign here, yeah, because 1 plus 2 is equal to 3, which is an odd number. So the cofactor will take the opposite sign. Okay, so to remember, normally, okay, we just put plus on the first element, then minus, and then plus on the third element, and then the sign will be alternate, plus, minus, plus, and then on one we have minus, plus, minus, then plus, minus, plus, yeah. That one will be helpful later when we want to find the cofactor. Okay, but for now, for the determinant, we we just find, using the formula, we just find the minor, meaning we delete the row and the column where the element is located and writing the remaining elements like this. Okay, so now when we have written this, we know already how to find the determinant for a 2 by 2 matrix. Just multiply 4 and 5 minus 2 times minus 1, or we get 2, yeah. So 20 minus 2. So we can do the calculation, finding the determinant for the second determinant and then the third determinant. Okay, once we get this, then we can calculate. So we get the determinant of A to be 52. Yeah. So 52, the determinant is not equal to 0. Therefore, the inverse matrix exists. So we can proceed to find the solution. Okay, next, we need to find the cofactor transpose, okay, for this matrix. So each element in matrix A has its own minor. Therefore, the matrix of minus is as follows. Okay, we just write the minus, and then, okay, to find M, for example, to find M23, this one, we delete row 2 and column 3. Then we take the remaining element, which is M11, M12, M31, M32, like this. Yeah, so this is what we'll get. Then this one, we can find the value by, this is minor is a determinant, so we can find a single value, yeah, by multiplying the two elements in the principal diagonal minus the product of the two of principal diagonal. So once you get all the minus, then you can get the cofactor by adjusting the sign of the minus. Yeah. So cofactor is equal to the minus with the correct sign. Okay, so that's why we just put minus on this element, on this value, and then minus on this value, minus on this value, and minus on this value. Once you get the minor, then adjust the sign. Immediately you get the cofactor. All right, now you transpose the cofactor to get this one. Okay, so still in symbol, that means the first row will become the first column, like this. Okay, so for example, for the 3 by 3 matrix that we have earlier, okay, 6, 3, 1, 1, 4, minus 2, and 4, minus 1, 5. Okay, the matrix of minus is as follows. Okay, then you can calculate everything. You will get this. Oh, sorry, this is the example, yeah. So I'm just showing this example M11. Okay, I think we know already, yeah, how to find. Delete row 1, column 1, so you get this 4 minus 2 minus 1, 5. Okay, so when you calculate, you get the first minor to be 18. Okay, putting everything together in the matrix of minus, this is what you get. To get the cofactor, you adjust the sign. Yeah, so you adjust the sign for 13, for minus 18, for 16, and for minus 13. Okay, depending on their position. So this is what we get. Yeah, 18 minus 13 minus 17 after you have adjusted the sign of the minus. Okay, like this. Since minor is 18, 13 minus 17, so once you adjust the sign, you'll get this, yeah? Okay, so now when you get the cofactor, you can transpose that. Change the first row into the first column like this. The second row into the second column, and the third row into the third column. Okay, so that is done already. Next, you can substitute everything into the formula to find the solution. Yeah, so I'm showing you the inverse matrix like this: 1 over 52 times cofactor A transpose. Okay, I'm just going to continue with this. I've shown you how to find the determinant and the cofactor. Okay, in fact, actually we can start solving a system of 3 equations in 3 variables. Okay, assume an economy has 3 commodity markets represented by the following system of linear equations involving the quantities of each commodity given by X1, X2, and X3. Okay, so the relationship between these 3 interconnected commodities are given in these 3 equations. So we want to find the equilibrium value of each commodity in the market. What are the quantities of product 1, product 2, and product 3 that will be produced in the economy? So since the equations are already written in the matrix array form, so we can just proceed to write the matrix equation form like this. So we have the matrix A times X equals to B. Okay. Okay, so the the determinant of this matrix is actually the same as the previous example that I've shown earlier. It is equal to 52 because this is actually the same coefficient matrix. Yeah, I'm using this when I showed you the determinant earlier. And then the cofactor A transpose is what we have obtained earlier, right? So to find the solution, we can just substitute everything into the formula like this. Okay, and then multiplying cofactor A transpose with the vector of constants, then we will get the sum, which is equal to 104, 156, and 52. Okay, and finally, we can multiply each sum with the number outside, which is 1 over 52. So 1 over 52 times 104 will get 2. 1 over 52 times 156, we get 3. And 1 over 52 times 52, we get 1. So the quantities, the equilibrium quantities will be 2 for x1, x2 equals to 3, and x3 equals to 1. So that will be the solutions that we wanted to find out, yeah, earlier. Okay, we still have time. Then I will show you an alternative solution method, which we call the Cramer's rule, Petua-Cramer. The method of matrix inversion discussed above enables us to derive a practical way of solving a linear equation system known as the Cramer's rule. So given a linear equation system in n variables, x1 until xn, so the matrix equation form will look like this. We have a11 until a1n, that is from the first equation. So you have x1 in the x2 until xn in the vector of variables, and in the vector of constants, you have b1 until bm. So this system has the dimension m times n, m equations, n variables, m rows, n columns. Okay, so the number of variables are 6, yeah? And we have b1 until bm. Okay, so the solution of the system can be expressed as xj star, meaning the solution for the variable that is located, that is identified by j, okay, by the column, okay, which is given by this, the determinant of aj divided by the determinant of a. Okay, now we can write this alternatively as 1 over the determinant of a times the determinant of aj. So this is equal to 1 over the determinant of a times the determinant of aj. The determinant of aj is equal to, okay, we replace the value of the constant in the column, which is equal to j. So if j is 1, that means we replace the constants, the value of the constants in column 1. If j is 3, then we replace the value of the constants in column 3. Okay, so let's try to solve an equation system, a 2 by 2 equation system. Solve the following system of equations using the Cramer's rule method. So for example, we have 2x minus y equals to 1, 3x plus 2y equals to 12. Since this is already written in the matrix array form, all the variables are written on the left-hand side, all the constants on the right-hand side, then we don't need to transform. Okay, we can directly transform the matrix equation, which is in the form of ax equals to b like this, yeah? So the coefficients, 2 minus 1, 3, 2, then the variables, okay, arranged in x first, y second, like this, and then the vector of constants, 1, 12. In step 2, once we have the matrix equation, then we can take the matrix of coefficients and find the determinant. This is to test for the existence of a solution, unique solution. Okay, finding the determinant, you get it to be 7. So the determinant is not equal to 0. We conclude that the inverse matrix exists and there is a unique solution to the system. So we can proceed to the next step, which is finding the solution. So in step 3, to use the Cramer's rule, then to find the first variable, okay, you have the determinant of A1 divided by the determinant of A. So to find the determinant of A1, replace column 1 of matrix A with the elements of the constant matrix P and recalculate the determinant. So once you have replaced A with the value of the constants like this, 112 in red color ink, then you can recalculate the determinant. So we get 1 times 2 minus 1 times 12. Okay, then you get 14 to be the determinant. Okay, to find y, which is the second variable, you need to substitute the value of the constants into the second column. Yeah, like this. Okay, so recalculate the determinant, then you get 21. In step 4, you substitute the values that you get, that you have calculated, okay, into the formula, then you get x star, which is the equilibrium value of x, will be equal to 2, and then y star will be equal to 3. Okay, so there is a unique solution, meaning there is one value for x and one value for y that will satisfy both equations simultaneously. Okay, we will see the application of Cramer's rule for a 3 by 3 matrix. Okay, again, let's use the same example as we have seen earlier. Okay, when we use the matrix inversion method, we still use these equations. Okay, so in matrix equation form, this is what we have. Next, okay, to find the 3 variables, okay, we have these 3 variables, right? X1, X2, and X3. So the arrangement is X1 first, X2 second, and X3 number 3 third, yeah. So in step 1, you find the determinant first. Okay, before trying to solve, we need to test for the existence of a solution. So find the determinant. We have seen, yeah, how to find the determinant earlier. So we just repeat this here. Okay, so the same step can be followed even when we use the Cramer's rule method. We can use Laplace expansion method. Okay, so the determinant is equal to 52. In step 2, okay, we just write the formula for each variable first so that we know what to find, yeah, what to calculate. So let's start by finding the determinant of A1. That means to solve X1 star. So to solve X1 star, you calculate the determinant of A1 by replacing column 1 of matrix A with the value of the constants like this. Okay, so once you have replaced that with the value of the constants, you can choose actually to find the determinant by expanding any row or any column. So let's start, let's say you choose to expand by column 3. So you have the elements 1, minus 2, and 5. Okay, adjust for the sign, plus, minus, plus. This is what? Third column, yeah. So the third column, the element is 1, then plus 2 because we have adjusted the sign, and plus 5. And then all these are the minus of that element. Okay, so once you have calculated all the determinants, the 2 by 2 determinants, you get this. Yeah, so the total will be equal to 104. Okay, next to find the determinant of A2, just replace column 2 with the vector of constants. Okay, once you have written that, you can find the determinant using any row or any column. Okay, let's say I choose row 2, yeah? So the elements will be 1, 12, and minus 2. Okay, I need to adjust for the sign, yeah, of the cofactor. To get the cofactor. So minus, I just put minus, plus, minus, and then the element will be minus 1 times the minor, plus 12 times the minor, plus 2 times the minor. Okay, now when you calculate that, you will get the sum to be 156. Okay, lastly, okay, you find A3 using the same process, yeah? You replace column 3 with the value of the vector, and then let's say I expand by the first row, yeah? So the sign will be plus, minus, plus. So just put plus 6, minus 3, and plus 22, and then times with their minus. Okay, so you get the sum to be 52. Okay, this one, let's say we use the expansion of the third column, yeah, when we calculate for A3, the determinant of A3. Okay, we can verify actually that the sum will be equal to 52, yeah. Okay, you should verify this answer. Actually, I'm just writing that, yeah. Okay, okay, so as a note, expansion of any row or any column should produce the same answer. So don't worry. That's why we can choose to expand using any row or any column that has the most zeros or the most ones. Yeah. Okay, number 3, we can substitute the values that we obtain in steps 1 and 2 to get the solutions of the variable. So we get x1 star equals to 104 divided by 52, which is equal to 2. X2 will be equal to 3 and x3 will be equal to 1. So we can verify that these values are the same, are similar to what we obtain using the matrix inversion method. Okay, so in summary, the steps to be followed in solving a system of linear equations for each method are as follows. For the inverse matrix method, step 1, test the determinant of matrix A. Okay, compare it with 0. If it is equal to 0, we do not proceed further because there will be no solution. We can just say that there will be no solution. However, if the determinant is not equal to 0, then we can proceed to the following steps. In step 2, we calculate the cofactor of matrix A transpose. And in step 3, use the formula to solve for the values of the variables. For the Cramer's rule method, okay, we in step 1, still the same step, which is testing for the determinant of matrix A and comparing it with 0, yeah, whether it is singular matrix or non-singular matrix. And in step 2, use the formula to find the value of each individual variable. Okay, so x1 will be equal to the determinant of A1 over the determinant of A. Okay, so this is the formula. Xj star will be equal to the determinant of Aj divided by the determinant of A. Okay, so comparing the matrix inversion method with the Cramer's rule method, in the matrix inversion method, we get all the values of the variables that we want to solve at the same time. But for Cramer's rule, we can find each value individually. Okay, so for example, if you only want to find the value for x3, then you can just calculate x3 using this formula. Okay, you don't need to calculate for x1 and x2. But for matrix inversion method, the solution will provide you with the values of all variables at the same time. Okay, so if the question only asks you for one equilibrium, one variable's equilibrium value. So you might want to use the Cramer's rule method. Yeah? So both methods have their own advantage. Okay, so that concludes my presentation today. So I hope, okay, so I thank you very much for attending the session, and it's been a pleasure, yeah, being with you today. So I hope the materials shared today will be helpful to you in your mathematical economics course with Dr. Dia, and in other courses, economic courses in particular as well. And also I wish all of you the best in your studies and in your future understandings. Okay, thank you very much, and I pass the session to Dr. Dia.
Thank you so much, Dr. Zalila. It's really focused on and really clear on the explanation concerning the matrices. If it doesn't have any problem, would you mind to share this material to the student? Is it possible, Dr. Zalila?
So yeah, it's possible. I will pass it to you after this. Through WhatsApp.
Okay, through
WhatsApp. No problem. Yeah.
Thank you so much. But I think I will open 5 minutes for students if you have any questions concerning the matrices.
Yeah. Okay. No problem.
Students, if you have any questions, you can raise hands or you just can open your microphone. I think everyone is really clear on everything.
Good, very good.
Or hopefully they are not sleeping.
We should ask them to open their camera.
Camera, yeah. I've already informed to open the camera.
They are too shy, probably.
Yeah.
It's
yes,
okay. Yeah.
Yeah,
okay.
I think the general problem on online.
Yeah. Okay, Dr. Dia, you need to continue with the rest of the session.
Oh yeah. Oh, sorry. We have
we have a question probably.
One question from Abdi Hakim Muhammad Ibrahim. So please, Mas Abdi Hakim.
Assalamualaikum warahmatullahi wabarakatuh. Thank you for your information. Second, I want to ask how this mathematics, matrix related to our course, economic.
Okay, is that all? Is that?
Yeah.
Okay,
yeah.
Thank you for it. Yes, thank you very much for that question. Okay, if you have a system of equations to be solved and all equations in the system are in linear form, okay, then you can choose to use matrix. Okay, so for example, you may have a market model where you have a demand function and a supply function to be solved. So if both the demand and the supply functions are given in linear form, so P to the power of 1, Q to the power of 1, then you can choose matrix algebra as one way of solving the system of equations. Instead of methods such as elimination of variables method or substitution methods, you can use matrix algebra. However, if the system of equations has at least one non-linear equation, then you cannot solve matrix algebra. For example, let's say P equals to 3Q squared plus 4. That means one of the equation is not linear. So matrix algebra cannot be used. So we must remember that matrix algebra can only be used for a system of linear equations. So we have many different models, like in microeconomics, you might have a firm that produce two goods or two products. So you have two equations, for example, okay, showing the two products. So we may use matrix algebra to use, yeah. So any kind of model where you have linear equations, you can use matrix algebra. Whether you use the matrix inversion method or you use the Cramer's rule method. In addition, you can use another method called the Gaussian elimination method. That is another matrix method. Okay, so in certain textbooks, they use that method to solve a system of linear equations. So I hope that answer your question, Abdi Hakim.
Thank you so much.
Yeah. Okay, welcome.
Okay, thank you, Dr. Zalila, and also Abdi Hakim. Okay, you still also raising your hand? You want to ask some questions again?
Sorry, I want to lower my hand.
Sorry?
No question. I think that was a mistake or something. Okay.
Okay. Oh, good. It's really nice to have you, Dr. Zalila.
Yeah, we can have this session often in the future. Since we have already started, then we may have sessions in the following semester.
I will arrange for our next having the collaboration for the teaching as lecturing for in our international program. So thank you so much, Dr. Zalila. Would you mind to open your camera, everyone? Let's have pictures together. It's really rare occasions to meet Dr. Zalila. Hopefully we can have the offline, so we can go to travel to Malaysia to meet Dr. Zalila.
I will be very pleased to have you here in Sintok, Kedah.
Yeah,
the north of Kedah.
Yeah, really hope to have to meet you in there or meet you in Indonesia.
Yeah, actually, I was in Indonesia in 2019 for the ICOR conference. In Jakarta.
In Yogyakarta.
Yeah, 2019.
2019.
When we have the conference, ICOR, International Conference on Entrepreneurship and Rural, I think something, ICORE.
Oh, I see.
Remember it now.
Wow.
I was there.
Yeah,
I didn't get to go to your campus. We had the conference in Jakarta itself.
Oh, wow. Is it UMY or other university?
I think with UMY.
With UMY.
Yeah.
Oh, okay. So but probably ICOC, because we have a one conference in every year annually, and we also have it again in this year.
We can we might go there, okay, if it's a conference and we can present paper over there.
That's good news if you can come here to join with us for the conference.
Okay.
Amin. Okay, everyone.
Okay, I can see the students now.
Okay, I can see students. Okay, I will count until 3 for doing the clicking the pictures. Okay. Okay, say cheese and smile. 1, 2, 3. Okay, let me make it in the here. Okay, once more. Say smile and cheese. 1, 2, 3. Okay. Thank you so much, everyone. And also, wow, Abdi Hakim. Finally, we met on camp. How are you there?
I'm good.
I'm good. Alhamdulillah.
Alhamdulillah.
Alhamdulillah, yes.
All right.
He's one of our foreign students.
Yeah. Okay, pleased to meet you guys.
Yeah, thank you so much. Thank you so much, Dr. Zalila.
Yeah,
So
so I
hopefully,
will probably leave now.
okay.
And probably I will see you in other sessions as well.
Okay.
Okay, I will remember to share the file with you later so that
yeah.
you can share with
Yeah.
the students. Okay, thank you
Okay.
very much.
Thank you so much, Dr. Zalila. We
Okay,
meet you again soon, inshallah.
inshallah. Bye. Assalamualaikum warahmatullahi.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for the students. Let's close with alhamdulillah, alhamdulillahirabbil alamin. We will meet you again in the next semester. Bye bye.